Okay, so welcome to the last recorded lecture for 11153 week 13. And it might be the final lecture for the whole course. So let's jump right into it. So our coverage for this lecture is actually on external peripherals and how to communicate with them. So why are we discussing this? So ang nakaraan na lectures are on digital and analog communication, or digital and analog signals, and ADCs and DACs. So bakit tayo napunta dito sa external peripherals? So as you may have noticed dun sa last part ng last lecture on DACs, our microcontroller doesn't have everything. One specific highlight is wala siyang digital to analog converter na uh, exact DAC as or true DAC for that matter, kasi meron naman tayong other techniques to generate digital analog signals, but wala siyang totoong DAC. However, ang PIC32 ang kaya niyang gawin is kumausap sa DAC or interact with these DACs and other peripherals na pwede natin gamitin that can help alleviate some load and help manage larger systems. So we can have a PIC32 na mag-communicate sa ibang PIC32, and for example, nasa smart farm, may PIC32 ka na nagre-record ng data, nag-check ng temperature, humidity, etc. And that PIC32, when it notices something wrong with the conditions, it will send a signal to another PIC32, and siya yung magkocontrol ng thermostat, or siya yung magkocontrol ng mga blinds ng windows for the light, siya yung magkocontrol ng temperature ng tubig, siya yung magkocontrol ng humidity ng room, etc. etc. So parang pwede mo hatiin yung mga tasks into different microcontrollers if medyo nagiging complex na yung system. So ayun, it can also help with other things like input. So wala naman thermostat, wala naman thermometer yung ating PIC32. So kailangan ng mga sensors. So usually hindi meron tayong mga digital na sensors and pressure meters, accelerometers, and etc. So baka hindi ADC yung kailangan to communicate with this, but with digital communication systems. So interacting with peripherals can start or can be accomplished through simple reading and writing on I/O pins. So kung ano yung mga keypads at saka LED display, pwede natin magamit yung mga to with general purpose I/O pins. And simple sensors like yung LM35 na gumagawa ng analog signal for a certain temperature. So pwede natin idaan sa ADC and magagamit na natin siya. But more complex peripherals would sometimes use what we call a direct memory access or DMA, which I think we discussed naman na before, wherein yung ating mga peripherals, they write on specific memory addresses sa ating PIC32. And this is actually used most probably in conjunction with the communication protocols that we discuss natin later on. But first, let's classify yung ating types of communication between devices. So first, we can categorize or group communication protocols through the number of data lines, or paano natin sinesend yung information natin, yung physical connection na ginagamit. So yung serial or series, we only use one data line and we send one bit after another. So we only use one wire, but it takes some time para masend natin lahat ng ating data. Then we have a parallel communication interface, wherein we have one data line or wire per bit, and bits are sent all at the same time. So this is much more faster kasi yung sabay-sabay silang darating. But it is more costly. So in this case, ang 5 bits of data, kailangan ng 5 cycles with a serial. Pero si parallel naman, kailangan natin 5 different wires. So for example, ang ating PIC32, yung nasa Curiosity Dev board, meron siyang 36 pins and some of them used na for power, for the ground, and dun sa ating other sensors or other outputs like yung LEDs, potentiometers, and switches. So baka yung 36 na yon, medyo it's a valuable resource, yung ating number of pins. So usually, kahit na mas mabilis si parallel, hindi natin siya kayang gawin because we don't have the pins for it. So the next thing we have here is, our next category we have is a synchronous or asynchronous na communication. So ang synchronous na communication, actually baliktad. Let me just annotate this para di kayo malito. So yung synchronous, ang receiver and sender natin have a shared clock. So we need an additional pin for this clock. But with this additional pin, we can reach higher speeds sa ating transmission. Kasi with the clock, alam ng receiver kung kailan siya nakakatanggap ng legitimate data with the clock signal. Sa asynchronous naman na communication, we need less resources. Actually, one less pin for the clock. However, kailangan yung devices natin magkasundo sila doon sa rate ng pag-send. And hindi natin siya masyadong pwedeng bilisan or tagalan kasi baka maging prone to overflow or mismatch. So may examples naman on this later on. But for now, kailangan tandaan, synchronous synchronizes sender and receiver by having an external clock. So si asynchronous, wala siyang external clock, pero nakakapag-send pa rin ng signals. And they accomplish this by, well, for lack of better term, tiwala lang na magsisend si sender at the specified rate. And basta nagkaintindihan doon. Then we can categorize communication interfaces by the direction of information. So meron tayong simplex na interface wherein yung data natin from one device to another na. And then meron tayong half duplex wherein pwede tayong mag-send from one device to another and from the another device back to the first device, pero one at a time. So pag nagsisend si pick 1 kay pick 2, hindi pwede mag-send si pick 2 kay pick 1. Pero pag walang nagsisend, pwede mag-send si pick 2 kay pick 1. And then lastly, yung full duplex na communication wherein sabay silang nagko-communicate to each other. So parang sagutan. And then next is we have communication interfaces based on the topology. So topology is how you arrange your devices and how they are connected with each other. So yung bus topology natin, meron tayong single line in the middle wherein connected tayo lahat doon sa tinatawag nating bus. Then we have a point-to-point na topology wherein one device is connected to another, or basically meron tayong connection from one device to all the other devices. So parang mas flexible to. For example, pwedeng hindi connected si computer na to sa computer na to. And ayun, para kumonect doon, kailangan mong mag-jump. So this is more of a network, and then this is more of a bus. Single. Then we have what is called categorized by access. So in a master-slave na setup, yung mga slave, hindi yan pwede magsalita unless bigyan siya ng permission ni master. So medyo self-explanatory naman. And yun, most of the time si master yung nag-initiate ng communication. And minsan nga yung mga slave hindi kailangan mag-communicate pa balik. Then we have what we call equal partners, wherein any device can initiate yung communication. So these are general communication terms, hindi lang siya applicable for microcontrollers. And ayun, In the system, kailangan meron tayong protocol na fixed sa kada isa para hindi tayo magkalabo-labo doon sa channel pag sabay-sabay nagsasalita. So parang meron yung token passing or na familiar kayo, wireless CDMA, division, code division multiplex. Basta yun. Equal partners. So a couple of terms, bit error yung tinatawag natin if yung tinransmit natin na information is different din sa na-receive. Self-explanatory. Then we have what we call the baud rate and the bit rate. So the baud rate is the speed of signaling events and the bit rate is the number of bits transmitted per second. So ano yung difference niyan? So itong usually yung baud rate natin is the same as the bit rate if ang ating signal event represents 1 bit. So yung usual naman. Same lang sila. However, if for example, yung signaling events natin could represent multiple bits, for example, 4 voltage levels. So for example, ang ating signal ay mukhang ganito. Pwede siyang bumaba. And then, for example, meron tayong 4 voltage levels. Actually, may 5. Let's say meron pang 0. So, pwedeng ito ay 1, 1, 1, 0. Ito is 0, 0. Ito is 0, 1. And then dito is 1, 0. And 0, 0 dito. So we can have different voltage levels. So yung baud rate nito is 1, 2, 3, 4, 5, 6. So for example, this is 1 second. So ang baud rate natin is 6 per second or 6 hertz. Or 6 symbols, pwede rin tawaging symbol rate. And then, ayun, in this case, we have 6 symbols per second. Pero ang ating bit rate, since ito, 2 bits at a time, so 2 bits per second tayo. 2 bps. Pero 6 SPS or SPS, pwede rin. Iba-iba yung term. But, ayan, ang baud rate natin is 6 per second, I guess. Around 6 hertz. And then yung bit rate natin is 12 hertz or 12 bits per second. Then we have the other case na pwedeng ating signaling events usually repeated multiple times to help reduce bit errors. So in this case, yung bit rate is na babawasan. So, for example, paano ba? Let's say, pag high to low, this is a 1. Pag low to high, this is a 0. So, pwedeng multiple ones muna. And before mag-send ng multiple zeros. So, basically, nagkakaroon tayo ng redundancy bits. Or in other cases, meron tayong extra symbols na hindi useful information. But it helps. So, ayan. For microcontrollers, we'll be looking at 3 common modules na ginagamit. And actually, for the PIC32, meron silang mga built-in modules for this. Unfortunately, sa PIC32MM, wala yatang I2C. But for the PIC32MX, meron siya. But we'll still go over all of them. So the first of this is the universal asynchronous receiver transmitter, or what we call UART. So UART is a serial point-to-point communication protocol and can use 2 wires for full duplex na communication or just 1 wire for simplex or half duplex. So basically, kailangan lang nila magkasundo na wag magsabay mag-send doon sa transmission line. And then our devices have to agree to transmit or receive at the fixed baud rate. So notice na yung ginagamit natin na term is a baud rate, it hindi bit rate. So ang typical UART na transmission would look something like this. So yung idle state natin is just high. And then meron tayong natawag na start bit or start sequence. And then magkakaroon ng transmission or yung data natin. And then we can have what we call a parity bit and then a stop bit before maging idle ulit yung ating data line. So kailangan magkasundo kung ilan yung mga stop bits tsaka yung extra bits na to, yung parity bit tsaka yung start bit. So ang parity, paano yung gumagana? So let's have 3 examples here. So ito is tinatawag na odd parity. Kailangan yung number of ones sa signal natin is an odd number. So here we have 1, 2, 3, 4. 4 1 bits na data. So para maging odd number yung 1, mag-a-add tayo ng 1 dito. Pag even parity naman, may 0 siya. Kasi 4 na siya. So even number. So to keep it even, may 0 yan. So this is used to check if merong bit errors. So if ang alam mo ang transmission natin is odd parity pero even number yung number of bits, that means na meron nagkamali doon sa transmission. Then we usually have a stop bit here. Ito 1 bit lang. And after that 1 stop bit, pwede na magkaroon ulit ng start bit na transmission. So if dalawa yung stop bit, dalawang baud period siya dapat naka-high bago magsimula ng bagong sequence. So, ang format ng ating transmission, kumari dito, 7 data bits, odd parity, 1 stop bit. This can be configured sa ating device. So, for example, the PIC32mm, we can have 9 bits of data, no parity, 8 bits of data, odd or even, or no parity. So basically, yung 9-bit data natin is sacrificing the parity bit for an additional data bit. And then, ayun, meron din tayong number of stop bits, either 1 or 2 stop bits for the topic 32mm. So meron siyang sariling module to set up this. And then, usually, ating microcontroller, meron din siya tinatawag na baud rate generator or BRG to calculate or generate the baud rate na kailangan natin for our UART transmitter. So, ito yung sa PIC32mm. Meron tayong 2 modes, BRGH equals 1 at BRGH equals 0. So, yung calculation ng baud rate is yung clock frequency, system clock frequency, divided by S. Si S determined, depende if high speed or low speed, times yung value na nakastore kay UXBRG. So, ayan. So, ito yung value ng BRG. Kung ano yung required na baud rate natin is 230 kHz. If we set UXBRG to 42, we get this 232 kHz. So merong konting error, hindi siya eksakto. Then, so parang table lang to of usually used na baud rates sa ating in the industry or in practice. So importante yung ating baud rate. Actually, mahirap tong merong konting error. So usually, you wouldn't want to use yung medyo matataas na frequencies or mataas na baud rate kasi mataas yung error niya from the actual sa baud rate na target natin. Because we can look at this example over here. If, for example, nag-transmit tayo at a certain baud rate and nagre-receive tayo at that agreed upon baud rate, so wala namang problem. Pero what if if yung baud rate ko is a bit faster, so yung BRGH ko is medyo mas maliit ng konti, so baliktad yata to. Ito yung mas mabilis, ito yung mas mabagal. So, unfortunately, hindi ko ma-edit. So, let me just draw over it. So, ito yung medyo faster. 1.05. And then ito si point. Ito si 0.95. So it's slightly slower. So if we are slightly faster over here, you'll notice na magkaka-time na. Dalawa yung na-sample natin for a single symbol and kulang tayo ng sampling ng stop bit. So mali yung nakuha natin na data. Then similarly dito, pag masyado tayong mabagal mag-sample, meron tayong bit dito na hindi na-sample at all. And meron tayong extra bit dito na nasa next transmission na. So a difference of around 5% dun sa ating baud rate is actually very dangerous when it comes to yung ating transmissions. So parang medyo delikado na nga itong 9% dito and 1.4% kasi kung hindi kayo pareho ng sender and receiver, probably baka magka-problems tayo dito doon sa sa ating sampling ng signal. So that is UART. So in summary, UART, siya yung simplest communication protocols actually. Simple lang, dalawang wire. Isang send, isang transmit, isang receive na wire. And then for each additional device, kailangan natin ng 2 additional wires at least. So point-to-point siya. For each device na gusto mong kausapin through UART, kailangan mo ng isang pair of wires. Then, ayun, ang baud rate natin, kailangan sakto talaga siya for each. So, kita naman dito sa example how difference of 5% can mean the difference between receiving a bit properly and not properly. So, kaya rin actually, medyo hindi recommended maging mabilis sa UART kasi nga mas mahirap maging eksakto sa frequency pag mataas na yung baud rate na tinatarget natin. So it is usually reserved for slower communications na ang habol talaga is yung minimum number of wires na gagamitin and hindi na kailangan gumawa or mag-generate ng clock signal. So ito yung ating simplest na asynchronous. So ang ating simplest na synchronous signal ay tinatawag na serial peripheral interface or SPI. So bus-like in a way and full duplex. So medyo may bus na connected sa kada slave natin. So in this protocol din pala, we have a master and a slave. So we have 4 wires to use for each, at least or minimum. So 1 wire for data input and 1 wire for data output. And then 1 wire for the clock and 1 wire for each slave. So 1 wire for each slave select na pin. So, ano nangyari dito? Yun pala, meron pa lang nakalito. MOSI, that means master out, slave in, master in, slave out. So usually yung gagawin ng master dito is siya yung magse-select ng slave na gusto niya kausapin and yung ating yung slave na nakaselect, siya lang yung makikinig dun sa wire natin. So a typical SPI signal will look something like this. So yung slave select, since may bar siya, active siya pag low. And then yung S clock, magsa-start siyang mag-trigger. Then we have a start sequence here. Ito is an address. And then, pwede, since duplex yung signal, pwedeng magsagot na si slave habang nagsisend pa rin si master. So, yun. So, yung data natin is sampled based on the S clock. And yung baud rate natin is dictated by the master. Kung ano yung generate na S clock ni master, siya yung susundan na baud rate ng ating slave. So, alam niya, in this case, pag nag-transition to high, doon tayo magsasample ng ating signal. So, for the SPI, we can actually achieve a higher baud rate by being synchronous. Kasi yun nga, hindi natin problema yung mismatch ng ating timing like we have in UART. So, rate natin dito is actually Kung dito either divided by 16 or 4, we have divided by 2 na lang. However, yun nga, kailangan natin ng 4 wires at the minimum and 1 additional wire for each additional slave. And if gusto mo maging creative, pwede kang gumamit ng decoder. So, kailangan lang natin ng log-based log n wires for n slaves. So, yung data amount naman natin in yung format is usually different across devices. So, walang standard na way or standard na framing na ating signals. Unlike sa UART na meron tayong start bit, stop bit, tsaka yung mga parity bits, and etc. Kasi sa UART kasi, since yun nga, walang clock, kailangan alam na ng devices beforehand kung ano dapat yung framing. Pero dito, yun nga, it's dependent sa communicate device. So that is SPI. So ang mahirap dito, ang daming wires natin kailangan, 4. So what if we use less wires? What if we want to use less wires? So that is where we use I2C. So sa I2C, it is a serial half-duplex synchronous communication protocol that fully utilizes the bus topology. So meron tayong bus over here, which is yung SDA, and it is a bidirectional bus. So we only use 2 wires, SDA, SCL, regardless of the number of devices. So, then, siya yung totoong bus kasi kada device na naka-connect dito, it can act as a master or a slave. So paano gumagana yung bus? So connected sila lahat. So paano nila malalaman kung sino yung kinakausap ng kada isa? So unlike yung SPI, meron tayong slave select. Dito sa I2C or I2C, wala tayong slave select. Pero meron tayong tinatawag na addressing. So meron tayong konting analogy dito on how the bus would work. So for example, ito meron, example, teacher, and kailangan may specific person siya na kailangan kausapin. In this case, Bob. So una, tatawagin mo muna si Bob. Tatawagin mo yung pangalan niya. And ayun, malalaman ni Bob na siya yung kausap mo. And hindi na, well, pwedeng hindi makinig si Joe at si Tom. Pero for sure, hindi para sa kanila yung sasabihin. So similar dito sa ating bus-based na communication, ang ating device or yung gusto maging master, sasabihin niya muna yung address ng gusto niyang kausapin. And yung other receivers, hindi nila papansinin since iba yung address na sinabi ni master. And yun, kung sino lang yung address ni master, siya lang yung respond. So yun yung basic principle ng ating I2C, paano siya gumagana. Yung ating signal will look like this. So our master will generate the start sequence. And una niyang isasend yung address doon sa SDA. Then, yung slave na may same address, magsisend siya ng acknowledge. Or, ang gagawin dito, after isend ni master yung address, bibitawan niya yung line. By bibitawan, magiging open circuit siya. So, si slave naman nun, kailangan niyang i-pull pababa para sabihin na na-acknowledge niya yung input. So, ayun. And then, for example, this is a sample signal for an EEPROM or basically memory, external memory. And kailangan isend ni master yung address. Parang 3 address bytes. And then, after nun, bibitawan niya, bibigay niya kay slave ay yung control doon sa SDA. And si slave naman yung magko-control ng signal. And then, magsisend ng response si master. So, ayun. So note here na parehong SDA pin to. Isang pin to, isang pin siya dyan. And meron tayong pull-up resistors dito para pag walang gumagamit ng pins, connected to VDD yung ating signal. Kaya ito, high siya kay master kasi hindi niya siya ginagalaw. And then, dito naman, high siya kay slave kasi hindi niya siya ginagalaw. So this is basically an open circuit. So it's the same line. So usually, mas mabagal siya ng konti sa SPI kasi yun, half duplex lang siya. As you can see here, hindi kayang mag-communicate sabay ni master at ni slave. So pag si slave yung nag-send, hindi pwedeng mag-send si slave. Eh pag si master yung nag-send, hindi pwedeng mag-send si slave. And pag si slave yung nag-send, hindi pwedeng mag-send si master. Pero effectively yung baud rate niya is nasa similar lang sa SPI. It's just that hindi kayang gawin sabay. So yung standard baud rates for I2C or I2C is actually 100 and 400 kilohertz. So this is lower than SPI. Since yun nga, kailangan natin yung same wire to respond. Isa lang yung pwede mag-communicate at a time. And meron tayong additional na time na devoted for addressing. However, it is still faster than UART kasi meron tayong available na clock signal. And yung clock signal na to is generated by kung sino man yung nag-act as a master for that current transmission. And then similar din yung actually yung computation niya for the baud rate. Ito yata +2 pero dito kay SPI +1 na. So ayun. So in summary, yung ating tatlong protocols. So UART, one wire for the transmitter, one wire for the receiver, and we have a baud rate of 4.8 to 230 kilohertz. So siya yung simplest protocol, but our devices na connected doon sa or nagko-connect to UART kailangan mag-agree doon sa timing. SPI uses the most number of wires. And the baud rate typically reaches 1 megahertz and even faster sa ibang devices. So yung most number of wires but achieves the highest baud rate. And yung pag-support ng multiple slaves, it comes at a cost of additional wires. So si I2C parang yung strength niya is yung weakness ni SPI. Minimum number of wires, 2 bus. Pero medyo malaki yung capacitance. Pero if you have the power, okay lang. Ang baud rate natin is 100 kHz or 400 kHz. So yan yung dalawang standard na baud rates. Yan. And then actually, it can support multiple slaves as well as multiple masters kahit magstay lang sa 2 wires. But ayun, meron tayong additional overhead sa addressing and hindi pwedeng mag-transmit ng sabay yung devices. So yun yung medyo trade-off niya. Less number of wires, but yun, parang nasa gitna siya ng UART at saka SPI. So mas mabilis siya ng konti kasi may clock kay UART, pero mas mabagal siya sa SPI kasi yun nga, nilimit natin yung number of wires. So in summary of the summary, meron tayong limitation sa ating own microcontroller. Kaya usually, we turn to help or we turn to other external peripherals for help in that regard. And in using these other peripherals, we will have to use a certain communication protocol. And kailangan pareho yung protocol na ginagamit ng microcontroller at saka ng peripheral kasi parang pag magkaiba, hindi sila magkakaintindihan. And choosing the right protocol is actually a big deal kasi yun nga, meron mga protocols na kailangan ng madaming wires or madaming basically madaming wires. And may mga protocols na mas mababa yung requirements of wires pero mas mabagal. So we have to find the right protocol for you para ma-maximize yung resources na meron ka and makatipid din sa mga resources na wala ka. So yun, mostly parang kwentuhan lang about trade-offs ng mga what's available out there. So ayun, maraming salamat for attending or viewing my lecture videos. Good luck sa upcoming quizzes and long quiz. And I think this is the last lecture unless mag-provide pa ako ng additional lecture for more examples. But I guess this is the last required lecture. Thank you very much for your time. And then, if you have any questions, just let me know. Merong forum, merong emails. And mahanap mo sa social media, you can also chat me. So, ganda emails. Anyway, that will be all from me. Thank you very much, and I'll see you around.